Hey guys, welcome to virtual biochemistry. This is primarily how we're probably going to run this is through these screen captures where you hear my voice talking over the slides, and then these obviously uploaded to my YouTube channel. We finished chapter 6 last time we were in class, so we're just going to pick up with chapter 7 because your upcoming test is going to be on chapter 6 and 7. And so obviously, you know, dates have been moved. Okay, so I'm thinking we're going to need 3 days to fully cover chapter 7. Plus, I want to be able to give you a virtual quiz before you get your virtual test. So we're going to allow 3 days for us to do chapter 7. So that means that we'll lecture on chapter 7 Wednesday, today, right? And then Friday, and then the following Monday. So basically, your test on 6 and 7 is a week from today. Okay, it is a week from today. So please make sure that you are talking to me if you have questions, and make sure you're using those discussions that appear under the assignments tab to discuss these lectures and ask me questions. Okay. All right. So we're going to move on and we're going to talk about sugar. Okay. So let's get this thing to work. All right. So this is just the basic outline. This is what's included in the chapter. We will be talking about all of these things in this particular order. Okay, but we'll start at the beginning with sort of some basic definitional stuff and then get into some nomenclature. So first of all, let's talk about the difference between carbs and so carbohydrates and glycoconjugates, because those are the two primary things that we're going to talk about in this chapter. So carbohydrates, right? Most abundant class of organic molecules found in nature. These are your sugars, right? So the energy captured during photosynthesis, it converts CO2 into the carbohydrates. But it's the breakdown of the carbohydrates that actually provides energy, which means you need to be eating carbs, right? Carbohydrates is sort of your long-term energy storage. Now you can overdo this and you can eat too much, but avoiding carbohydrates altogether is not necessarily a good option either, right? So don't buy into all the fad diet nonsense and just portion control, right? Don't cut carbs out of your life. All right, glycoconjugates. So these are the carbohydrates that are linked to something else. And notice it says covalently linked. So we're not talking about just a little bit of a hydrogen bond interaction here. We are talking about a covalent bond through a glycosidic bond, which we'll talk about when we get to them, okay? So these are important structures in cell walls, extracellular structures in plants, animals, bacteria. They serve all different types of recognition roles. Like I said, we'll talk about these a lot more later on. We're going to start by focusing the chapter on carbs. So your lecture today is going to be primarily focused on carbs. So what are the basic features? Well, they're metabolic precursors of basically everything. So what does that mean? They're the energy precursors of all other molecules. Carbs are associated with energy, okay? That's why if someone is feeling super tired, what do? You jump on a little bit of sugar, right, to give you that energy boost, okay? Carbs are associated with energy. And there are sort of 4 characteristic features associated with them. So a cool thing is the fact that they have at least one, if not 2 to 4 or more asymmetric centers. So there's a lot of R versus S stuff going on here. But, you know, if it has 4 asymmetric centers, we don't want to have to label each one. So we'll get to how we just call them L versus D and which one we actually look at to classify, right? Because if there's more than one asymmetric center, then how do you know if it's L versus D? We'll talk about that later on in this lesson. They also have the ability to either be in linear or ring structures. Those are going to have very different interactions with solvent, right? So it's kind of cool that they can wrap up or they can choose to be linear depending upon their needs and functionality needs. They have the capacity to form these really long polymers, right, via these glycosidic bonds, which again we'll get to probably next lecture, okay? And as I said before, they can form hydrogen bonds with their environment, which in the body is going to be water. And this is a really good thing because this means that our carbs are water soluble, okay? Why? Because they have all different types of polar groups on them, right? And water's polar, and if they have polar groups, then that's going to be a lovely little interaction. Okay, so let's talk about some nomenclature. So our carbs are either going to be classified as a monosaccharide, a oligosaccharide, or a polysaccharide. These are the exact same types of nomenclature that we use when we talked about peptides, right? So a mono meaning one, so this is just a singular unit of a sugar. Oligosaccharide meaning you have anywhere from 2 to 10, so just a few of these sugar residue units linked up. So this would be like a oligopeptide with a few amino acids, or polysaccharide where you each have a long chain, which could be branched or linear, right? Of up to thousands of these monosaccharide units. So again, very similar nomenclature to what we did with peptides, so not really reinventing the wheel here at all. Let's look at its general formula though. So here's the general formula that all carbs have. So you're going to have a carbon and it's going to be double bonded to an oxygen. Remember, carbon's going to have 4 bonds. So there's 2 bonds right there. Then it's going to have a single bond to each of these 2 hydrogens. There are your 4 bonds. And then we're just going to repeat this. Or and or and or and or. And that's what makes up our sugar. Okay, let's look at some pictures. So here are some pictures of the 2 major types of monosaccharides that we have. And these monosaccharides can have anywhere from 3 to 7 carbon atoms. The aldose and the ketose here that we're showing you are both examples of trioses because they have 3 carbons in the backbone. Now, how do you tell the difference between the 2? For those of you who've taken organic chemistry, you're already familiar with these aldehyde ketone functional groups. If you didn't take organic chemistry, let's talk about it, right? So what these functional groups are is they all have a carbonyl group in the center, which is a carbon double bonded to an oxygen. So what a ketone is a ketone says it doesn't care what those other 2 single bonds are. They could be to methyl groups, to something like this, right, which is super complex. It doesn't really matter, okay? It's going to be something more complex. Whereas an aldehyde is going to say, okay, one of them can be complex, but the other one needs to be a hydrogen. Okay, so this is your aldose. So you've got your complex R and then your singular hydrogen. It is an aldehyde, whereas this is your ketose. It contains a ketone because here's an R group attached to the carbon and here is an R group attached to the carbon. Okay, these are really important as far as metabolism. Again, these are giving us our energy. The most common though is 6 carbons. So a 6 carbon backbone, which we would call a hexose. And a hexose, the 2 most common examples of that are glucose and fructose. So you guys consume glucose and fructose on a regular basis, right? So very, very common, and these are by far the most abundant sugars in nature. All right, so let's talk about some nomenclature stuff. So let's start with the simplest problem, which is going to be a triose. Okay, so let's start with a triose, meaning there are 3 central carbons, 1, 2, 3, 1, 2, 3. Now, if it is a triose for the ketose, right? For the ketose, meaning you have an R group on either side. In this case, the R group's exactly the same. So there is no L versus D here. This is just dihydroxyacetone, and that is its name because the R groups are exactly the same. There's no sort of stereocenters here at all, okay, that you could change. Now, let's look at glyceraldehyde, which is the simplest aldose. This one does have some stereocenters. Here's your stereocenter right here. The hydroxide could be on the left or the hydroxide could be on the right. All right, we have to decide L versus D. Well, if you remember, L clockwise, D counterclockwise, but for that to work, the hydrogen needed to be pointed backwards. But in a Fisher projection, I hope you remember, and it's sort of classified here, that the hydrogen is pointed forwards. Okay, so that means everything we've known has been flipped. Okay, so you will always start with this functionality here at the beginning. That's your number 1, and then we're going to move in the direction. So the hydroxide is a higher priority than our CH2OH group here. So 1, 2, 3, going from high to low, and then the hydrogen would be 4. We just went counterclockwise. That's a problem, right? Nope, because remember, the hydrogen's coming forward, not backwards. So it flips the rules. So counterclockwise is L in this case for official projection. And then here, starting with high, 1, 2, 3, we just went clockwise, 4, but it's okay because the hydrogen is coming forward, so it flips it. All right. Let's look at some bigger ones, right? Because this is the real big issue as far as stereo centers are concerned. Because take a look at this. This is fructose. This is 1, 2, 3, 4, 5, 6. 6 different carbons. Okay, so this is a hexose sugar. Like I said before, fructose is a hexose. But take a look here. You've got 3 stereo centers. All right, because the hydroxide could be here, 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 here. You've got a lot of options here. So how are we going to name this? How is this D-fructose? How do you know? Because any one of those 3 could determine if it's L or D. Well, what we say is that we're going to determine L versus D by the configuration of the highest number asymmetric carbon. Which one's the highest? The carbon that's furthest from the carbonyl. All right, so this is your carbonyl. So let's get as far away as you can get. This is it. Okay. So in this case, the hydroxide is on the right, the hydrogen is on the left. When the hydroxide is on the right in a Fisher projection, this is always going to be a D. Why? Because the hydrogen is coming forward. We're starting with sort of this being our 1. Okay. So 1, 2, 3. We just went counterclockwise. Or sorry, we just went clockwise, but that's okay because remember the hydrogen is coming forward, so that flips our rule. So that is D-fructose. If you put the hydroxide on the left, it becomes L-fructose. Now, this is different than your amino acids because what do we say about amino acids? For amino acids, L predominates in nature, but for sugars, D predominates. Okay, so they are not the same. L predominates for amino acids, D predominates for sugars. Okay, that is different. All right, so that was your, if we go back, this here, we're looking at some sort of, we looked at one example of a ketose. Now we're going to look at more examples of a ketose. Okay, so here is your simplest one, right? Now we move on to a tetrose. Okay, so a keto tetrose because we have a 4th carbon in here. And now that you have the 4th carbon, you can have L versus D. Remember, D is what predominates in nature. How do we know this is a D? Because we have to go clockwise, which means D in this case. All right. And then when you add another stereocenter, so you add a 5th carbon, so this is a ketopentose, now all of a sudden you have 2 options, right? Because for it to be a D, we only look at the asymmetric carbon that's furthest away, right? So the hydroxide's on the right, so this is D. Hydroxide's on the right, so this is D. But you don't care about the previous asymmetric carbon. So it could be on the right or on the left, hence 2 names. So it splits. So what you're noticing is every time you add an asymmetric carbon, you get 2 structures as an option. Okay, so then this is D-ribulose, and if you add a 6th carbon center onto this, your options are D-fructose or D-pisticose, which is a very weird name to say. Or if you have D-xylulose, that can go down into D-sorbose and D-tagatose. Okay, so it's an interesting idea when you consider this sort of asymmetry that's happening at every single carbon and the fact that we only consider the bottom one to classify it as L versus D. It means that we sort of have this exponential increase in numbers of structures, which is really cool. Okay, and I'm explaining the colors here, right? So yellow is the sort of, so pink is the highest asymmetric carbon, the yellow is the new one we're adding, and then blue is highlighting the most common ones. Okay, and these are simple monosaccharides, so they are water soluble and they taste sweet. And this is the end of video